Okay, so here we have a wave that is trapped within the length. What you'll see is looking along, we've got sections which have a maximum vibration, so the actual displacement that it works through reaches a peak here and then a negative peak, and in between it's moving up and down. However, you're seeing the maximum distribution there. Now that's the maximum displacement, so that's its amplitude. This one has a different maximum amplitude because it's smaller. So all of these will reach the top at the same time, reach the bottom at the same time, but actually what you'll find is that even though they're moving together, some of them move further than others. This is known as an antinode, and that's because it's the opposite of this. So this is a node, this is a very definite point, that's quite curved, so it's quite hard to find, but this is a very definite point, and what we've got is absolutely no movement going on. There's still two waves, there's still waves shooting up and down, but there's nothing going on at that point. We then go on to another antinode, another node, another antinode, and of course a node, because at the end where it reflects it can't move up and down, so that's got to be a node. So here to here is 1/2 wavelength. Okay, so I've got another half wavelength node to node. So from these I can actually work out what's going on. We have 90 centimeters or 0.9 meters. If I look on my scale for my signal generator, we have 1.5 there, so that's 15 hertz. And because I have 15 hertz, and we have a wavelength of, as I say, 90 centimeters per half, so 2 times 0.90 equals 1.80 meters. If I put those together, then obviously I can get the speed of the wave. Okay, and that is the speed of the wave traveling up and down this string. If I make it tighter, like a guitar string, I get a higher note, and that's because I actually have a faster wave. These have to change because of the faster wave. So let me go up. This is actually the second harmonic. This is not fundamental. I can't quite go low enough. But if we go up in frequency, you get constructive and destructive interference until you get to the next point, where again you get nice clear maximum somewhere around about there. Okay, there we go. Bit too far. So this is now at 2 hertz. Sorry, 2 times 10, so 20 hertz. Okay, again the scale's not great, but from this what I can do is relate this again. So what I've done is I've added in another half wavelength. So before I had 2 nodes, I've now got 1, 2, 3 nodes, and of course the ones at the end as well. Okay, so my harmonics means a shorter wavelength so that they fit in an extra half wavelength each time. Okay, so from this one I can repeat my readings. I'm now at half wavelength of 68, so a full wavelength of 130, actually that's a better reading, 137, so 1.37, and you can see, you know, that has gone up, so that one's gone down. And if we add up to the next frequency, we can keep repeating these. Again, this will fade away and you get a bit of a mess until you hit the next resonant point, which is looking about there. So again, I've now added in 1, 2, 3, 4, 5, an extra node and an extra half wavelength. Okay, so I can keep repeating those readings, but it's all about the speed at which it travels up and down. And if you do the mathematics with both of those, you'll find that you basically get the same speed. Now, we said that was the speed of the wave travelling up and down. If you watch this in slow motion, I'll slow this down in the video, but you can actually see this in real time. If I just twang the string, you can see the ripple spread along and spread back. Okay, so what I'm doing is I'm starting to build up that wave, that trapped wave in here. And the reason it works is because I've actually got 2 waves. When I ripple this, wave races up, it hits the end, it flips over, so if it was going down, it then starts on the top as it comes back, and it's coming along. But each time that's vibrating, that's still sending ripples out. As they reflect back and forth and cross over, they cause that interference. Okay, that superposition. In places they superpose to always cancel out at the nodes, and other places they always superimpose to give the maximum. That's the antinode. Okay, to take our standing waves in strings a bit further, what I've got here, similar kind of setup to the white string, wire this time, so it's a bit more tense. I've got a fixed mass of copper, so we'll come back to that in a bit. But I've set it up with the right frequency, which at the moment is 45 Hertz, and what that gives us is a standing wave that is one wavelength. If you look along here, we've got a node at this point. Okay, we've got an antinode here, and then a node at the end, node at this end. And what I've got at the end is I've got a little bit of tension. Okay, so my tension in there is what's making the string vibrate at this frequency. Okay, to make the standing wave fit. So we'll just let that build up again, have a little bit of a fiddle to make sure we get the maximum there we go. So that's at 44 Hertz, let's say correctly. So 44 Hertz, and that's because the tension on the end of the string, the weight on the end of the string is 400 grams. Now I'm going to say that's the mass, of course, in grams, but what we've got is our actual weight, which we can work out our tension from the weight. Okay, so I'm going to put in equals mg underneath. Tension in, as I say, in newtons, and our frequency in hertz. Now, that's to make our experiment work. We're going to keep a fair test. We're going to keep the same wavelength. Okay, but I've now gone up to 600 newtons. Now, because of that, 600 grams, so around about 6 newtons, a bit under. So I'm going to have to adjust the frequency, and what I'm going to actually have to do is I'm going to have to turn this up, because if you think like a guitar string, the tenser it is, the higher the note. There we go, that's just about right. So again, we've got the node exactly the same position, which is at 131-ish centimeters for a half wavelength. So what I've got there in terms of our frequency is I've now gone up to 54 Hertz. Okay, so I've gone up by 10 by increasing the mass on the end by around about 50%. Okay, so 54 Hertz. Now if we go up again, and we'll go up to 800. So we go up by the same force again. You'd expect it, if you took a first instance, to go up by the same amount in frequency. But that's not quite true. Okay, it's not a linear relationship. Fairly big. Nice and steady. No, that's too far, so turn it back a bit. Okay, getting larger, getting larger, getting larger. And when those antinodes are as big as they can be and you've got a nice clear node in the middle, that's, I think we've got a bit of drift going on with our signal generator. Okay, that's looking pretty good, and that gives us 61 Hertz. Okay. And that's for 800 grams on the end. Now if we go to 1,000 grams, again it's dropped out ever so slightly there, you can get the idea. If we go to 1,000 grams, again if this was lab work I'll be getting you to do much more readings and I would get you to do repeats, but if I turn up in frequency again, then we should again be able to fit just the same amount. I think I've gone past it there, so I shall go back down to 61. Now, because it's tenths or tenths, it's going to be harder to find this. The vibrations won't be as big. Gone way past. I just might have it just 2 tenths to actually pick out those notes. We're getting harmonics appearing, and that's around about 65 hertz. But yeah, we've suddenly jumped into harmonics, so not a valid amount. That what I'll do is take it back down, take one off. We've got 900 grams rather than 1,000. Let's see if we have any better luck with that. So we go up from our last reading, which was 61 hertz. It's around about there. But again, we're not getting valid results there. Okay, so not going to give us valid result today. So if we turn that off, we can use that data. Again, we can take some results from that. If we work out those, so again 9.81 multiplied by 0.4 kilograms, 0.6, 0.8. What you'll start to see is that the velocity is proportional to root of the tension. So the higher the tension, the higher velocity, which is why you need a higher frequency, and divided by what's known as mu, which is the mass per meter of the wire. If I had a thicker wire, it would give me a lower note. And again, with guitars, bass guitars have much thicker strings, so that gives them that lower range of frequencies. So if I do that, I can obviously put frequency times wavelength, because that's equal to velocity. That's actually going to give us that exact value, so T over mu. And what I could do, as I say, if I take that measurement that I had there, which is 1.31, well, that's going to be half of the wavelength. So if we had 2L, where L was the length I've just measured there, times by frequency would give us that. Or more conveniently, if I move up to the top here, what we have is the frequency we get from our notes is 1 over 2L, because I'll take that across, the square root of T tension over mu. And that is in the notes, okay, to give us an idea, but it gives you that idea of what things give us different notes out of vibrating surfaces. In this case it's a string, but you could have the same thing making aircraft vibrate or wings vibrate in flight and things like that. About the tension, the forces within it, and the mass of it. The bigger the mass, the slower it's going to vibrate.